So in today's session we continue with power system stability analysis. So in the last session we did the power system stability analysis. A few topics like analysis of steady state stability, swing equation, how we apply swing equation to the steady state stability. Now we continue our today's session with transient stability, the analysis of transient stability. Now you know the swing equation. How you represent the swing equation? M d square delta by dt square is P. Now the stability of a synchronous machine depends on the solution of swing equation. And the solution of swing equation depends on the number of synchronous machines in the power system network. Number of synchronous machines in the power system network. The stability of the synchronous machine depends on the solution of swing equation, and the solution of swing equation depends on number of synchronous machines. Now first we consider single machine system. So what about this single machine system? You consider an alternator connected to a transmission line, further an infinite bus bar. This is the infinite bus bar. This is the reactance of line. This is the reactance of generator. So how you obtain the solution of single machine system? By a mathematical technique known as elliptical integral method. By means of a mathematical technique known as the elliptical integral method. Now you consider a two machine system. In two machine system you consider an alternator connected to a synchronous motor, connected to synchronous motor. And how you obtain the solution of swing equation for two machine system? It is obtained by a graphical technique. What is that most popular graphical technique? Equal area criterion method. So what is that graphical technique? Equal area criterion method. And third one is multi-machine system. Multi-machine system means you form an interconnected grid here. You form an interconnected grid. Then how you obtain the solution of multi-machine system? By a mathematical technique known as point by point method, or you also name it as step by step method. Point by point method, or you also known as step by step method. Now, when you consider a two machine system, both machines have equal size. In a two machine system, when you consider a synchronous generator and a synchronous motor, both have the equal size. When the size is same, moment of inertia is same. Therefore, the frequency of rotor oscillations is same. So, you can consider a two machine system as one machine system. So, what you can do now? You can consider a two machine system as one machine system. That is, if synchronous generator is stable, then synchronous motor is stable. If synchronous generator is unstable, then synchronous motor is unstable. That is, you say that both machines swing together. We mentioned that both machines swing together. So this is the analysis of a two machine system. Now we discuss what are the assumptions of transient stability. Now, based on this assumption, we further check what can be the maximum power transmitted before fault, during fault, and after fault. Now, first we discuss assumptions of transient stability. Now, the first assumption is the mechanical input to an alternator is constant. Mechanical input to an alternator is constant. Mechanical input to an alternator is constant. Now, second one is the angular velocity of rotor is constant, because whenever fault occurs, the changes in the angular velocity is negligible. So, angular velocity of a synchronous generator or alternator is constant, because changes in angular velocity is negligible during fault conditions. Now, second assumption is angular velocity of a synchronous generator is constant, since the changes in angular velocity is negligible during fault conditions. Negligible during fault conditions. And you know, alternator also has a third winding, that is damper winding. So the damping force provided by the damper winding is negligible. That is, damping force cannot oppose the swinging of the rotor. So you say that damping force is negligible. So now you say that the damping force provided by the damper winding is negligible. That is, you say that the damping force do not oppose swinging of rotor. Do not oppose the swinging of rotor. Now the voltages across the reactances of synchronous machine are assumed constant because change in the voltages are negligible when compared to change in the reactance of the line. Change in the reactance of the line. So what is the fourth assumption? Changes in the voltage across the reactances in a power system network is negligible because changes in the voltages are negligible when compared with changes in the reactances of power system network. And fifth assumption is the resistance and reactance of transmission, the resistance and conductance of transmission line are negligible. Or you say the resistance, conductance and shunt elements are neglected. And the shunt elements are neglected. And in such case, what is the next step? You determine and or you say model the remaining network with a transfer reactance. What do you mean by transfer reactance? The reactance between the source and the load by eliminating fault point. You define as transfer reactance are neglected. And further what we say? The remaining network is modeled as the transfer reactance. That is, the reactance between source and load by neglecting the fault point. So these are the assumptions of transient stability. Now these assumptions we always implement whenever we analyze transient stability of the system. Now we solve this next question. So a power system network is given. One at angle 0, 0.1, here 0.1, 0.2, 0.1, 0.1, 0.2, 0.1, 0.25, here 1.2 at angle delta. And these are the values given in the question. Now further it is mentioned that a fault has occurred at the middle of one of the parallel transmission lines. Fault has occurred at the middle of one of the parallel transmission lines. Now we have to calculate what is the maximum power transmitted before fault, during fault, after fault. So we have to complete these three calculations. Now first we represent electrical power transmitted before fault. How you represent that electrical power transmitted before fault? PE1 is EV by X1 equivalent sine delta naught. PM1 sine delta naught. And what is X1 equivalent here? X1 equivalent is the equivalent transfer reactance. Is it before fault or after fault? Before fault. Now you change this as before fault. And what is PM1? Maximum power transmitted before fault. And what about this PM1? Maximum power transmitted before fault. Now we mention what is electrical power transmitted during fault. You indicate with the subscript 2 now. PE2 how you write? EV by X2 equivalent sine delta. That is PM2 sine delta. And what is X2 equivalent now? X2 equivalent is the equivalent transfer reactance during fault. And what is this PM2? PM2 is the maximum power transmitted during fault. Next one is electrical power transmitted after fault. So PE3 how much? EV by X3 equivalent sine delta. So you mention as PM3 sine delta. And in this notation, what is X3 equivalent? Equivalent transfer reactance after fault. So PM3 is the maximum power transmitted after fault. It is the maximum power transmitted after fault. Now again we relate these quantities here. For any faults, the line-to-line faults, you know that during fault less power, after fault further it is before fault. So how to also reload this before fault? PM2, how to write? PM2 is EV by X2 equivalent. So you multiply and divide with X1 equivalent here. So what will be this now? Some ratio, say R1. EV by X1 equivalent is PM1. PM3 how much? EV by X3 equivalent. Or you say E1 EV by X1 equivalent. Now you multiply and divide with that value. Now say this ratio is now R2 into PM1. Now you know that PM2 is less than PM3. On the same lines, now what you get now? R1 is less than R2. On the same lines, what you get? R1 is less than R2. And now we will find out first before fault. What is the maximum power transmitted? So how to analyze what is X1 equivalent? The total reactance before fault. So what we have? Two lines. This is 0.4, this is 0.4. Both are in parallel. That side 0.25 is in series. And to this side we have 0.1 here. So how much you get now? It is 0.55. Now once you know X1 equivalent, how to find what is PM1? EV by X1 equivalent. 1.2 into 1 by 0.55 here. So what about PM1 now here on simplifying? On simplifying you get it as 2.18 per unit. All these values in the questions are in per unit place. So what is PM1? 2.18 per unit here. So each and every quantity in the question are by default in per units place. So they are by default in per units. Next question, next one is after fault. During fault we will find further, but after fault how to find X3 equivalent? Now important point, now fault is cleared. But immediately as soon as the fault is cleared, you cannot transmit power through this second line because this line must be synchronized with the synchronous generator. Only after the synchronization is completed, you can transmit power through this line. I repeat, you are checking after fault condition. Now once the fault is cleared, you cannot immediately transmit the power. Now, once the fault is cleared, immediately you cannot transmit the power. When you can transmit the power, not only fault must be cleared, but this line must be synchronized with synchronous generator. Then you can transmit power through this line. But the standard assumption regarding after fault is, after fault means fault is cleared. The assumption is, assume that transmission line is not synchronized with synchronous generator. So what is the assumption here? The transmission line after fault is cleared is not synchronized with synchronous generator. So you cannot transmit power through this line. Then what is the reactance left out here? 0.4. What about this side? 0.25. And here it is 0.1. How much you get now? That is 0.75 per unit. How much you get? 0.75 per unit. Now how to calculate what is PM3? EV by X3 equivalent. How much you get on simplifying? 1.6 per unit. And now we have to check before fault. Now before fault we have 2.18, after fault 1.6. Now we will check during fault. What is the maximum power that can be transmitted? For that, you reduce this network now. So we have 0.25. This total how much? 0.4. And what about this side now? 0.2. This side is 0.2. Now you got a delta configuration here. So we have to confine the delta, now convert the delta to star. So how you convert the delta to star now? So you are having delta configuration. How much here? 0.4, 0.2, 0.2. Now you should convert this to star. So how much each of the star values we have to calculate now. Now this one connected here, 0.4 side and 0.2 side. So star how you write? R12, R13 divided by the total sum now. How much you get? 0.1. What about this one now? 0.4, 0.2. Denominator is the same. What about this one now? 0.2, 0.2. The denominator is again the sum. 0.05. So this is how you convert the delta into star. So 0.05, 0.1, here it is 0.1. So 0.25, this side is 0.1, here 0.05. What about the next one now? 0.25, 0.1 are in series. How much you get now? 0.35. Here 0.05. Here it is 0.2. Now you find the transfer reactance, that is the reactance between the source and load, by eliminating fault point. So how in the process of getting that reactance, you convert again this star into delta. Convert again this star into delta, but you require only this reactance X2 equivalent. So what is the transfer reactance? The reactance between source and load by eliminating fault point. Reactance between source and load by eliminating fault point. That is, you have to calculate X2 equivalent. So this side we have 0.35. This side you have 0.2. Now to this you add their product and divided by the missing one is 0.05. So now we simplify this one and find out 1.95 per unit. Then we can calculate what is PM2. How much you get? EV by X2 equivalent. X2 equivalent is 1.95. So you simplify this one, you get the answer as 0.615 per unit. You get the answer as 0.615 per unit. So this is how you analyze whenever a fault occurs on a middle of a transmission line, that is before fault, after fault, during fault. What is the maximum power that is transmitted? Again you can verify the answers here. You get PM2 less than PM3 less than PM1. This relation is however satisfied for any numerical or for any data given in the question. Now we check. Whenever you consider a two machine system, you can have a coherent swinging of two machines or non-coherent swinging of two machines. Now we check. What do you mean by coherent swinging of two machines or non-coherent swinging of two machines? Coherent swinging of two machines. So you consider an alternator, another alternator, connect to a common bus bar here, so meeting a load demand P load. Say now it is the synchronous machine 1, this is the synchronous machine 2. Now assume that the load demand has increased. Now before increase in the load demand, what about the stator and rotor axis of synchronous machine 1? You can represent like this. This is the stator axis, this is the rotor axis. What about this angle now? You represent as initial load angle delta naught. Same thing for synchronous machine 2 also. First we have stator axis. Next we have the rotor axis. Initial load angle is delta naught. Now when the two synchronous machines are swinging coherently, the increase in the load demand is equally shared by both synchronous machines. Increase in the load demand is equally shared by both synchronous machines. So the change in the position of rotor with respect to stator is identical. So change in the position of the rotor of synchronous machine 1 and synchronous machine 2 are identical. That is, you say this delta 1 is same as what? Delta 2. Say it as some value delta now. So what is the statement of coherent swinging of synchronous machines? Due to increase in the load demand, the increased load demand is equally shared by the synchronous machines in parallel. By the synchronous machines in parallel. So what will be the PA now? You have delta 1 is equal to delta 2. So you write PA1 and PA2. So what about this PA1? M1 d square delta 1 by dt square. And further, what about PA2? M2 d square delta 2 by dt square. This we write M equivalent d square delta by dt square. Now delta 1, delta 2 both are equal. Delta 1, delta 2 both are equal. So add these two terms, M1 plus M2 d square delta by dt square. On simplifying this, what is M equivalent? M1 plus M2. You know that M and H are directly related. What is H equivalent? H1 plus H2. Now you consider for n synchronous machines, what is M equivalent? M1 plus M2 so on up to Mn. What about H equivalent? H1 plus H2 so on up to H. So this regarding the coherent swinging of synchronous machines. Now we check the non-coherent swinging of synchronous machines. Now we check non-coherent swinging of synchronous machines. Again you consider two alternators in parallel. So initial load angle is how much? Delta naught. Say now the load demand has increased. Now when coherent swinging of synchronous machines exist, the increase in load demand is equally shared by the two synchronous machines. With non-coherent swinging of synchronous machines, the increase in load demand is shared by only one machine. The increase in the load demand is shared by only one machine. So machine 1 takes the entire increase in the load demand. So only the position of rotor with respect to stator changes for machine 1. For machine 2 there is no change. So what is the equivalent delta now? It is delta 1 minus delta 2. So on further deriving, you get the relation as 1 by M equivalent is 1 by M1 plus 1 by M2. So M and H both are directly related. 1 by H equivalent, you write 1 by H1 plus H1 plus 1 by H2. Suppose you consider two synchronous machines, n synchronous machines. So what we have now? For n synchronous machines, 1 by M equivalent is 1 by M1 plus M2 up to 1 by Mn. Then what about 1 by H equivalent? 1 by H1 plus H2 up to 1 by H. This for non-coherent swinging of synchronous machines. And what is it? By default we assume whether coherent swinging or non-coherent swinging, always we assume coherent swinging of synchronous machines. So always we assume coherent swinging of synchronous machines. So this regarding coherent swinging and non-coherent swinging of synchronous machines. Now we solve these questions. The moment of inertia of 200 MVA generator is 10 per unit. The moment of inertia of 400 MVA generator is. So this is what we have to calculate here. So how M and S are related? They are related directly. So M1 you say proportional to S1. S1 is 200. M2 proportional to S2. S2 is 400. Divide these two terms and calculate. M2 by 10 is 400 by 200. On simplifying, what is the value of M2 you get? M2 you get it as 20 per unit. M2 value you get it as how much? 20 per unit. Next question is the inertia constant of a 100 MVA generator is 4 per unit. So now we have to check the inertia constant of 200 MVA generator is. Inertia constant of 200 MVA generator is. So how S and H are related? Inversely related. So firstly 4 per unit, and further you don't know, but it is 200 MVA. How much you get? 4 into 100 is H2 into 200. On simplifying, what is the value of H2 you get? H2 you get the answer as 2 per unit. So what is the value of H2? It is 2 per unit. Now we solve this next question. A 200 MVA alternator is having a inertia constant of 8 megajoules per MVA. So now you mention the kinetic energy stored in the rotor at synchronous speed is. So what will be the kinetic energy stored? S into H. So you know this formula. Accordingly you calculate. You get the 1600 megajoules. How much you get? 1600 megajoules. So you consider the generators G1, G2, 200 MVA, 11 kV, H values are given. 100 MVA, 11 kV, 20 megajoules per MVA. So now the question is the equivalent inertia constant based on a common base of (400 MVA) is. So H value we have to calculate now. First to check for G1 how H and S are related, inversely related. So initially it is given 10, S is 200. With respect to 400, we have to find out for the generator G1. So how much you get? You get it as 5 megajoules per MVA. It is 5 megajoules per MVA. Similarly for G2, H inversely proportional to S. Now it is given 20 and 100. What about further for 400? H2 for G2 you have to calculate. 20 into 100 is H2 for G2 into 400. From this you check what is the value. You get it as 5 megajoules per MVA. So what is the equivalent H value? You add those two values of G1 and G2. 5 plus 5, how much here it is? 10 megajoules per MVA. How much you get? 10 megajoules per MVA. So this is how you calculate and find out what are the corresponding values of H here. Okay, we continue after 5 minutes break. First question is by Ajit from Jaipur. What are active and reactive power basically? See, we have the network elements, resistor, inductive reactance, capacitive reactance. The power due to resistance is active power. Power due to reactance, say inductive reactance or capacitive reactance, is reactive power. Next question is by Somdev from West Bengal. We know that inductance is, and two formulae you have quoted. So if you want to calculate the inductance per phase, 2 into 10 power minus 7 natural logarithm of d by r dash. For loop inductance or circuit inductance, 4 into 10 power minus 7 natural logarithm of d by r dash. So 4 means loop or circuit inductance. Next question is by Vishwam from Agartala. Do we always have to perform star to delta conversion 2 times for calculating equivalent reactance during fault? Yes. And do we always eliminate fault point for calculating equivalent reactance? Yes, during fault you calculate the equivalent reactance by eliminating fault point. Next question is by Pooja. How to find transfer reactance in the numerical taken for transient stability? See, it is simple. Last step, convert that star to delta. Next question is by Somdev from West Bengal. How you convert delta to star? Simple delta to star conversion formula only, please. So first reactance outright, multiply other two reactances divided by the total sum. Simple network formula only, please, not any new formula. Next question is by Vishwam from Agartala. Is rotor angle same for both machines during coherent swinging? Yes, it is same. Next question is by Sanjog. In question number 2, is m moment of inertia and how m is proportional to s? You know the formula in the last class you have derived. M is equal to sh by pi f. Next question is by Vishwam from Agartala. Always by default we assume swinging to be coherent. Correct. Next question is by Pooja. Please explain the derivation of non-coherent swinging. See, derivation you please refer any of the standard textbooks. Next question is by Shubham. So still I have to solve the numericals, please. In that you can post your question again. I will solve in that section.